And now for the solutions to the E3 reflections, our topics are primarily experiments, surveying, sampling, and of course hitting some old stuff as well. So the first question, which of the following is a method for improving the accuracy of a sample? Well, accuracy has two components. One is removing biases. So I don't really see any of these options that have a lot of biases. Using no more than 3 or 4 words in any question doesn't really affect the accuracy. So that's not a bias issue. When possible, avoid the use of human interviewers, relying on computerized dialing instead. That's not a bias issue as either. Because just because you have human interviewers doesn't mean you're going to have more biased, okay? And in fact, you might have some non-response bias based on computerized dialing. Use larger sample size. Larger sample size helps with precision and variability, not necessarily with bias. If you have a biased design, it's still there. Use smaller sample sizes, always a worse choice. Never use smaller sample sizes if you can use larger ones. Ask only questions for which the responses are quantitative variables, also not an issue of bias. So the only thing I see, accuracy has 2 parts, getting rid of bias and then minimizing variability. One of these does minimize variability, and that is using larger sample sizes. Number 2, in an experiment, an observed effect so large that it would rarely occur by chance is called, well, might be tempting to say that it's an outlier because it says rarely occur by chance, right? But the effect is large. So that's not typically what we're looking for in an experiment, all right? It's not an outlier. Influential, I could see why you'd be tempted, but we haven't really learned correlation yet. We'll learn that next unit. So we heard about influential points, which, by the way, are outliers. Statistically significant means that it is very unusual and we weren't expecting it, so it makes us change our mind. So that is the correct answer, all right? It is statistically significant. So when we see a difference so big from what we would predict, that is statistically significant. Bias, again, that is not bias can be, it's not about rare. Bias is actually pretty common, unfortunately. And replication is just about getting ideally larger sample sizes or larger experimental groups, or maybe repeating experiments. Number 3, all the players on a JV soccer team for one school in the district participate in the study. The players were asked if they wore the flash shoes. They were then divided into 2 groups based on their answer to this question. The running times for both groups are recorded. What conclusion can you make based on this particular study? So 2 things we always have to figure out is who are the participants. In this case, they're all of the players on a JV soccer team for one school. Since it's like limited to one group, it's almost convenience, we can only infer to that group, okay? We cannot infer to everyone. Then the other thing that we can decide is the study an experiment or is it an observational study? Well, they were asked if they wore the flash shoes. So we can just talk about association. This is an observational study. And we cannot talk about causation. So you can see A, D, and E all say causes. B, C, and F all have association. And we're only saying players on this team. So that's who we can infer about. It's just the players on the team. And we can only say association. Number 4 in the study, so same study, one half is randomly assigned to wear the flash shoes and the other half keep their same shoes. The running times for both groups are recorded. So here we have a random sample of soccer players in the district. So we can actually say, because it's a random sample and we're assuming minimal bias, that they are representative of all soccer players in the district. So for the players at this district, which means we're either choice A or choice C. And then we randomly assign the shoes, so then we can jump all the way to causation. B says association, and A says causes, and so we can't jump to that. And so we got we've got randomly assigned, and it is A, and the other one said association. For players at this District C, there's an association, but we actually randomly assign, so we can jump all the way to causation, which is the ideal, if we can actually determine cause. So now we have the same, another study. Random sample soccer players in the district were asked if they wore the flash shoes. Then they were divided into two groups based on their answer. So we're still inferring to the players in the district. I can infer to them all because I took a random sample. And we just asked. So this is an observational study, so it's association. So you can see I've got A and C for players at this district. One is causation, one is association. We go with the association choice. There is an association between faster running times and wearing the flash shoes. Number 6, different design. One half is random. So we have a random sample of soccer players at one school. One half is randomly assigned to wear the flash shoes, and the other half keep their same shoes. So who can we infer about? We can infer about all soccer players at the school, even though we did a random sample, because we're hoping it's representative, and then we randomly assign. So it's school and causation. So that looks like choice E. Number 7, a study of elementary school children ages 6 to 11 find a high positive correlation between shoe size X and score Y on a test of reading comprehension. The observed association is most likely due to, well, so shoe size and reading comprehension, gosh, hopefully you would figure out a 6-year-old probably doesn't read as well as an 11-year-old, and a 6-year-old probably has a smaller foot size than an 11-year-old. So it is not cause and effect. It is effect of another variable, such as age. This can be a confounding variable. To conduct a survey on holiday shopping patterns, a researcher opens a telephone book to a random page, closes his eyes, puts his finger down on the page, and reads off the next 100 names. Which of the following is not a true statement? So, let's see. Does the survey incorporate chance? It does, because you don't know where he's going to point. He just points somewhere in the book. Does the procedure result in a systematic sample? Actually, he's just picking one and he's starting there, so I'm going to say that is not true. It is not a systematic sample. And the procedure could easily result in selection bias. Absolutely, that is true. He could, odds are they're going to be kind of people in the middle, because when we randomly pick between left and right, we almost never pick far left. We almost never pick far right. We tend to go in the middle and we think that's random, but it's actually biased. We tend to be more towards the middle. The procedure is not a simple random sample, definitely not. And the use of a phone book will result in undercoverage bias because, shoot, have you even seen a phone book these days? Phone books used to be just landlines, so when people started getting cell phones, most of us got out of the phone book. But even before then, poorer people would not be in the phone book, and maybe very rich people who had private telephone numbers would not be in the phone book. So there you go. You end up with some biases. Suppose the average score on a national exam is 500 with a standard deviation of 100. If each score is increased by 20, and then that result is increased by 10%, what are the new mean and standard deviation? The increase of 20 affects the mean, but not the standard deviation. First of all, remember, when we go and we take statistics and we kind of crank them through something, either like adding two measurements or using a formula, and this is a formula, then we're either combining or transforming. In this case, we're just transforming. So transforming means the math is easier, and the mean's going to behave very well. But the standard deviation, we just look at things that multiply or divide. We don't look at add, subtract. So the new mean is 500 plus 20, right? And then the 10% increase is like multiplying by 1.1, so multiply both the mean and the standard deviation. So your new mean, the final mean, is 572, and your final standard deviation is 100 times 1.1, which is 110. So there you go. Number 10, the yearly average rainfall along the coast of Liberia is 210 inches. What is the standard deviation if 20% of years have rainfall under 200 inches? Assume yearly rainfalls are normally distributed. So I'm going to use Staplets so you have a nice picture, and then I'm going to show you the calculator notation. So we don't know this. We don't know the standard deviation. So I cannot go into Staplet and say, oh, the mean is 210, and then standard deviation, well, just leave that blank. I don't know what it is. Staplet has no idea what to do. So in cases like that, I have to use the standardized form, where the mean is 0 and the standard deviation is 1. So the standardized form is a z-score of 1. All right, so I put in my mean of 0 and my standard deviation of 1, and I want the area to the left, so under 200 inches. I want that to be 20% of the area. So you see I put 0.2 in, and I get a z-score of negative 0.842. Now, if you're doing that on the calculator, you would just say inverse norm, left area, and you can actually specify, on the newer calculators, you can specify left, central, and right. If you have an older calculator, it defaults to left only. So we have negative 0.842, and so now we can use our equation, substitute in, multiply both sides by standard deviation, and of course I subtract 200 minus 210, gives me negative 10, divide both sides by negative 0.842, and I get 11.876, which is 11.88 inches. Number 11. An advantage to using surveys as opposed to experiments is that, yeah, surveys are cheaper. That's the main advantage of using a survey. Now, sometimes you don't really want to determine cause and effect. Experiments are about getting to cause and effect, all right? So let's look at the rest of the choices. It is generally easier to conclude cause and effect from surveys. Actually, you cannot not do that. You can only do that with experiments. Surveys are generally not subject to bias. Oh, sure they are. Lots of bias in surveys. In fact, if you design a good experiment, that's probably less likely to have bias. Surveys involve use of randomization. So do good experiments. Surveys can make use of stratification, and that's true, but guess what? In experiments, we don't call it stratification. We call it blocked design. So that's kind of like stratification for experiments. So the correct answer on 11 is A. Surveys are generally cheaper to conduct. When controlled experiments are impractical or unethical, which of the following would be necessary to establish a cause and effect relationship between two variables? So there are times that we can say, okay, there really is a cause, even from an observational study, because, for example, initially when we're first looking at COVID, you don't want to throw people in a room with COVID back in the day before we had proper treatments for it. And even that now we try not to expose people. So they would use observational studies because that's the best they had. So if you were stuck with observational studies because you just couldn't do an experiment for one reason or another, you can still try to infer cause and effect. It's unusual, but it happens. You need super strong association. So it has to be like, oh, wow, look at that. And then it's observed that that association is between those variables is in many different settings. The cause is plausible, and there are no other obvious variables whose effect is confounded with the explanatory variable in the study. So all of the above, you need to do all of those things. Problem 13. An experiment was conducted to investigate the effect of a new weed killer to prevent weed growth in onion crops. 2 chemicals were used, the standard weed killer S and the new chemical N. Both chemicals were tested at high and low concentrations on 50 test plots. The percent of weeds that grew in each plot was recorded. Here are some box plots of the results. So you can see, okay, there's my new chemical, and there's my standard weed killer at low concentrations. So you see we have slightly higher weed growth here, which makes sense. Lower concentrations, less weed death. Higher concentrations, less weeds. More weeds die, right? So which of the following is not a correct statement about the results of this experiment? At both high and low concentrations, the new chemical results in better weed control than the standard weed killer. So remember, there's a not with an underline there, and it looks like the new does tend to have less weeds in general than the standard. So this is true. This is true, so it's not our answer. Be careful, we do this all the time in stats. For both chemicals, a smaller percentage of weeds typically grew at higher concentrations than lower concentrations. Well, let's see. Here's lower concentrations. We tend to have more weeds. Here we tend to have less weeds when we have higher concentrations. The higher concentration box plots are shifted left for both of them, so that's true. The results of the standard weed killer are less variable than those of the new chemical. Yeah, the standard, you can see it here and here. There's less variability, so that's true. High and low concentrations of either chemical have approximately the same effect on weed growth. B is true, so D can't be true. We just said that higher concentrations of chemical, either the new or the standard, you have less weeds, so they're not the same. That's false. And so that's our answer, but let's look at the last one just to be 100%. Some of the results for the low concentration of weed killer show a smaller percentage of weeds growing than some of the results for the high concentration. Well, that's true. There is overlap. So some of the results for low concentration show a smaller percentage of weeds. So the minimum is actually here for the new chemical, the low concentration, than it is here at the high concentration. So absolutely, that is true. So our answer is B. That's the only false statement among our choices. If the heights of a population of men are approximately normally distributed, and the middle 99.7% have heights between 5 and 7, what is the standard deviation of the heights in this population? Ooh, I must like getting standard deviation from two values. So what we can do is, first of all, we're going to figure out the z-score for the middle 99.7, all right? It's negative plus or minus 2.968 if you said your central area was 0.997. By the way, that should also look a lot like the empirical rule. We're going to just say plus or minus 3. All right, and my mean is 0, and my standard deviation is 1. So here you can see this is the other way I could get those z-scores, negative 2.968. And there you go, and you can see it goes just almost to negative 3, not quite. All right, so now we know our z-scores. We can also figure out our mean, because we know that this is split even centered about the mean, 5 feet and 7 feet. I'm going to change those to inches. So this is 60 inches and 84 inches. Hopefully you're cool with that. So the mean is 60 plus 84. If you're wondering, I just multiplied both of those by 12. Divide by 2, and I get 72 inches. So the mean area is 72 inches. All right. Now, I can plug into here. It doesn't matter which one I do. I could do the left one, or I could do the right one. Most people are more comfortable with positive values, so I'm going to put in the higher value because that's the one with a positive z-score. So 3 equals 84 minus 72 over SD. Multiply both sides by subtract that out, and then multiply both sides by SD and divide by 3, and you get 4 inches is your answer. 15. Suppose that a student is randomly selected from a large high school. The probability that the student is a senior is 0.22. The probability the student has a driver's license is 0.30. The probability that the student is a senior or has a driver's license is 0.36. What is the probability that the student is a senior and has a driver's license? So I'm going to use a Venn diagram for this, but you could use a table, all right? If you need me to show you a table, you can bug me in tutorials or maybe even bring it up during class. Or comment. If I get enough of you say, I want to see the table version of this on this reflection, then I will show you the table one, all right? So, but right now you're getting the Venn diagram. So here I got my Venn diagram. I've got seniors and people with driver's licenses, right? So what is the probability a student is a senior and has a driver's license? So I'm looking for this sort of central area. There we go. I'm looking for this central area right here. Now, what's one of the things we know? We know senior or driver's license is 0.36. So both of these combined, everything in here should add up to 0.36, which means everything outside must add up to 0.64 because 0.36 and 0.64 add up to 100%. Now you're probably going, why'd you do that? There's actually multiple ways to tackle this one, and this is how I chose to do this one. All right, so the outside area we know is 0.64, which is funny because it looks like less than half the area, but that's fine. All right, we know the probability of a senior is 0.22. All right, so these two pieces combined is 0.22. So I'm not ready to put 0.22 here or here because I don't know how to split them up. Now, I also know the probability that they're not a senior is 1 minus 0.22, it's 0.78. Now, how does that help? Well, I already know 0.78 is going to be this piece right here plus the outside piece. But I know the outside piece. The outside piece is 0.64. So I can just take that 0.78, subtract 0.64, and that tells me this piece right here is 0.14. All right? Which means, since I know that the whole driver's license is 0.36, I could just figure out, driver's license is 0.30. I said 0.36, didn't I? 0.30. Then I can go ahead and say, what has to go here to make this whole area 0.30? And it would be 0.16. So 0.16 is the area in the center there. Voila. Last problem. 17 people have been exposed to a particular disease. Each one independently has a 40% chance of contracting the disease. A hospital has a capacity to handle 10 cases. What is the probability that the hospital's capacity will be exceeded? So this is a binomial distribution because we have exactly 17 people. The probability is independent. It's the same. It's 40% or 0.40. We're worried about exceeding 10 cases. So we're looking for the probability that X is greater than 10, not X is equal, but greater than. All right. So if you put this in the Statlet, and don't worry, I'll show you the calculator. If you put this in the Statlet, you have 17 and you have 0.4, and you can see that we would expect about 6.8 people to actually get the disease, which makes sense. That's 40% of 17 people, right? And the reason I keep showing you the Statlet is I want you to see this distribution. So you can see that on average, most of the time, it's going to be less, 10 or less, and the hospital's fine. The problem is when we hit number 11, where are we going to put them? In the hallway? I don't know. Maybe a nursing home. They did that, by the way, during some of the COVID. So you can see we have definitely some probability of 11 or 12. 13 is pretty small. And when you add these all up, you get 0.0348. All right, so the answer is 0.0348, also known as 0.035 right there. But let's go ahead and make sure you know how to show this using a calculator because you're not going to get to use the Statlet on your AP exam. And eventually, I may block this part of the Statlet, and you may not have access to this later after you get used to doing these on the calculator. Don't worry, you got it this fall. It's not a problem. Okay. So we have a probability that X is greater than 10. That's the same as 1 minus this probability here. Now, why am I doing that? Because your calculator doesn't do this piece. It only does left-sided cumulative probabilities. It only knows how to start at 0 and go up. It does not know how to start at the max and go down. Okay? So, since I'm reworded it, so I'm looking for this piece to start, that's binom CDF, not to be confused with PDF, because it's cumulative. It starts at 0 and it goes up to 10. And then I just put my n equals 17, p equals 0.4, and x equals 10, because that would be all this dark blue piece right here. All right. Make sure you label n, p, and x if you're using calculator notation. Then I put that in my calculator, and there it is, 0.96518, blah, blah, blah. Subtract that out, and you get 0.035, which is your answer. Now, again, if you need me to show the table for the other problem, leave a comment in the feedback of what you learned or what you